Okay, let's get started with class for today. Okay, so we're gonna finish up chapter. So we're gonna finish up chapter 6. We still have 2 sections left, so we kind of got through half of it, and it was covered by the exam last week. Does anyone need the notes from, I guess, like 2 weeks ago at all? So there's only 2 parts of it that are and then we're going to go into positive definite matrices that was Yeah, so we're still looking at eigenvalues and factors as well as applications. There's really just 3 weeks left of the semester, pretty much. I think it ends on May 4th, or classes end on May 4th, so there isn't that much time left. I'm still not decided if the final exam is going to be cumulative or not. I feel like it would be. I feel like people generally don't like it when it is cumulative. But as time goes on, the material gets more difficult. So it's like it'd be nice to have like a row reduction problem on there, probably. I don't know. That's kind of like my feeling on it. It is worth just as much as the midterms. So wait, you have to get up, and I'm not gonna. Actually, I don't. Oh, it's right here. Yeah, so it's yeah, it's worth as much as any of the other midterms. So I'm not going to plan on making it like usually the final exams are like maybe twice as long or 1.5 times as long. It's not going to be much longer than an average exam. Like the average exam so far has been like 5 or 6 problems. The final is probably going to be 5 or 6 problems as well. You'll just have more time to do it. It doesn't really make sense to have it be twice as long, despite the fact that it's worth as much. So I haven't written the final, obviously. I don't know exactly how I'm going to handle it. I haven't really determined exactly like what material. I want to focus more on applications as we go on. Next, or I guess this week on Wednesday, we'll talk about something called singular value decomposition, which shows up a lot. It's like one of the most important applications in linear algebra. It's like pretty essential in data science and machine learning. So I want to spend some time looking at applications, maybe like principal component analysis or something like that. I might go into neural networks a little bit. Just to show like how it works via matrix multiplication and stuff like that. So what do you see on the schedule? I don't know if anyone looks at the schedule, probably not, but it's probably going to be different from what's on the schedule. I want to go into applications a little bit. But for now, we're just going to finish up what we were doing a couple of weeks ago. So chapter 6 has kind of been like the eigenvalue, eigenvector section. So we started looking at symmetric matrices. And these symmetric matrices tend to have really nice properties with respect to eigenvalues and eigenvectors. This is going to be explored further when we talk about the singular value decomposition. But it really just comes down to the idea that if we have that S is a symmetric real matrix, and we have that these 2 eigenvectors, V1 and V2, have different eigenvalues, then it turns out that the vectors are going to be orthogonal to one another. So as long as you have distinct eigenvalues, you have orthogonal eigenvectors, which means that you have a basis of eigenvectors, in other words. So it pretty much means like you're going to have diagonalizability, right? So these symmetric matrices, as we'll see later on, are always going to be diagonalizable, which is a very nice property. So we prove this. I'm not going to say everything that we've done. Right, like the main point is you can choose the eigenvectors for a symmetric matrix, so that way they're going to be orthonormal via the Gram-Schmidt method. And then I think the last thing we did was this example at the bottom of page 6. And the main point of this example was just illustrating that you can have a matrix with real values, like with real entries, that nonetheless has complex eigenvalues. So we found the eigenvalues of this matrix ended up being 1 plus I and 1 minus I. Therefore, you also get eigenvectors that have complex values associated to them as well. So just because you have real values doesn't mean you can't have complex eigenvalues. But what we ended up finding is that the eigenvalues you do end up finding, as well as the eigenvectors, are complex conjugate to one another. So the only difference between these eigenvalues is the fact that one's plus, one's minus. And then similarly for the eigenvectors, you have plus here and minus here. So that means they're complex conjugates to one another. And so another nice property of these symmetric matrices is that they're only going to have real eigenvalues. You don't have to worry about complex numbers at all, which is really nice. And so we're going to prove this. This proof is a little bit, I don't like it very much. It's kind of just like, it's a little unintuitive, I think. This isn't something you would have to do on an exam because it's a little bit long and unintuitive, I think. But I'm going to start off by saying we have this matrix S that's real and symmetric. It's an n by n matrix. And we're going to suppose it just has some eigenvalue lambda. We don't really know anything about lambda, but we're just going to say with S times V is equal to lambda times V. And then just as a reminder, we're going to be looking at the complex conjugate. So what the complex conjugate does is if you have a complex number, if you take the conjugate, it just changes the plus to a minus. So this becomes A minus B times I. And so what we're going to do is we're going to take this equation and we're going to take the complex conjugate. And what we want to do is we really just want to show that this lambda is going to be a real number. So eventually what you want to do is you want to show, so kind of like the goal here is the following. So we have the following goal, which is you want to show that lambda ends up being equal to the complex conjugate of lambda, right? If you have that lambda is equal to its complex conjugate, then that means there can't be like a complex component to it. So you only have like a real part to the eigenvalue. We're not going to do too much with complex numbers. So like if this is kind of like, I don't remember the complex conjugate or how complex numbers work, it's not going to be like, when we move on to the next section, we're not going to really be looking at complex numbers. So if this is like a little confusing, it shouldn't worry you too much. And so we're going to take the complex conjugate of the equation that we started off with. And then we're just going to mess around with a couple of things. So if we take the complex conjugate of this equation that we have here, the complex conjugate, it turns out it distributes over multiplication. So you can say this is like if you had the complex conjugate of the left-hand side, it ends up being this product, and then it's going to be equal to the complex conjugate of lambda times the complex conjugate of V. So I'm just applying the complex conjugate to this equation. And we know that S is a real symmetric matrix, meaning that all the entries of S are real numbers. So the complex conjugate doesn't have any influence on it. This only has an influence if you have, again, a complex component. If you have something being multiplied by I that you're adding to it, right? So the complex conjugate doesn't do anything to S because S just has real values. And then this is where it gets a little bit unintuitive. In order to kind of move things around a little bit, I'm going to introduce the transpose and see what happens. And it also makes sense to use the transpose because we know that S is symmetric and you want to be able to make use of that in some capacity. And so I'm going to apply the transpose to this equation. So this is the same thing as having S times V conjugate transpose is equal to lambda conjugate times V transposed. And so we know what the transpose does to matrix multiplication, right? This is technically like the product of two matrices. So you switch the order, like you apply the transpose to both terms in the product and you switch the order. So this is the same thing as having V bar transposed times S transposed. And then, I mean, what's going on here? Lambda is just a number, so the transpose doesn't do anything to it. I mean, it's a number transpose is just a number, like it's the same number. It's like a 1-by-1 matrix is how you can think of any number. So if you take the transpose of a 1-by-1 matrix, it's the same thing over again. So this is like lambda bar, and then this is like V bar transpose. But then again, like we said that S in the beginning was symmetric. So if you take the transpose of S, it doesn't do anything. So I'm just going to erase the transpose here. Again, the transpose for a symmetric matrix, like that's the definition, doesn't change anything. And so what I'm going to do now, this is like another kind of and maybe it makes sense, but maybe you wouldn't think to do it immediately. I'm going to multiply the right-hand side, like on both of these equations by v. The reason why I want to do that is if I multiply this equation by v, it's going to introduce this equation over again. So I'll be able to bring like a lambda back. All right, question.
For lambda bar.
Mhm.
So we established that the transpose like makes them flip.
Mhm.
Why didn't we like jump the order? Like
Wait, why is the
lambda bar
order?
is just a number, and then S, the transpose doesn't affect S. So why are we even switching? Why are we switching one side but not the other?
Oh, I mean, this is matrix multiplication. Like this is a matrix. This is a vector.
Okay.
This is just a number. So like you can bring the scalar anywhere you want. Like it doesn't really influence anything. So like this is like you should view this as like matrix multiplication, and this is scalar multiplication. Yeah, it kind of gets like as time goes on in this class, it kind of gets harder to kind of sort like all the variables and like what they represent. What I'm gonna do is I'm gonna take this equation. I'm gonna introduce a v on both sides. This will make it so we can bring lambda back into the fold and then eventually compare it to its conjugate. And you want to be able to say they're equal to one another. And so you have v bar transposed s, and then I'm going to multiply by v. And what you do to one side, you have to do to the other. Right, so I'm just introducing a v on the right-hand side on both equations. And then the reason why I did this is this s times v, because lambda is an eigenvalue with eigenvector v, we can rewrite this as being lambda times v. And so you get something like this. And we're getting close to reaching the point, right? Because at this point, like these two things are very similar to one another. If I bring the lambda outside like this, what we've really concluded is that we have that lambda times v conjugate transpose times v is equal to lambda bar v transpose or v bar transpose times v, right? So like these things are very close to one another, right? Like we did a couple of manipulations, we moved some things around, and now we have like lambda and lambda bar, and they're both being multiplied by the exact same thing. And so what we want to be able to do to finish this problem is we want to be able to divide by v bar transposed times v. And divide's the right word because this is a dot product, right? Like if you do one vector transpose times another vector, as long as the dimensions match up, like this is just going to end up being this is just a dot product. So this is just going to give you a number. And so we need to ensure that this is going to be a non-zero number. Right. And so how I'm going to write this out is I'm just going to say like v1 is equal to how do I want to do this? Not v1. I'm going to say like v is equal to like v1, v2. So these are the components of your vector. And then if you do v bar, it's the same thing over again, except like these numbers that you have for your components, you're taking the conjugate of each of them. And so if you do the following, so if you do v bar transposed times with v, again, it's the same thing as just doing the dot product. So this is going to be equal. So you could write it out in this way. It's the same thing as doing v1 times v1 bar plus v2 times v2 bar, all the way up until the nth part, which is going to be vn times vn bar. And we want to say that this is going to be non-zero. And so maybe you know this, maybe you don't. But if you look at a number and you multiply it by its conjugate, this is what ends up happening. So just kind of as an aside, if you take any number and you multiply by its conjugate, so you just FOIL things out, so you'll get a squared, you'll get a minus a times b times I, and then you'll have a plus a times b times I, and then you're going to have bi times minus bi. Because you have the I squared, it introduces a minus 1, and so this ends up being equal to b squared. And so these terms cancel out with one another. This ends up just being equal to a squared plus b squared. right? So the main point I'm getting at in writing this out is as long as A and B, or as long as A or B are not equal to zero, this is always going to be greater than zero, right? Like as long as you're like, as long as A and B aren't zero, this term is always going to be greater than zero. So as long as V is non-zero, which we always, I think in like throughout the mathematical community, they always assume like you can't have zero eigenvectors. So as long as V is not zero, this term or like this sum here is going to be greater than zero, really from this observation here, right? You're just taking a number, multiplying by its complex conjugate. From this observation, it's going to be greater than or equal to zero. And if V is a non-zero vector, one of these has to be strictly greater than zero. So this ends up being greater than zero. And so then if you divide both sides of this equation by this product here, you get the following. So dividing. So this is verifying that it's like legal to divide by this quantity here. So if you divide this equation by V bar transpose times V, you end up getting the following. So if you divide by V bar transpose times V, it's going to end up yielding that lambda is equal to lambda bar, which then implies that lambda is a real number. Again, this one I think would be a little bit, it would be way too much for an exam, obviously, because there's a lot of steps to it. And I don't know, there's a lot of different components and it's a little unintuitive in terms of like why we're introducing certain things. But the main point is we wanted to be able to compare lambda with its conjugate and say that they're equal to one another. These things are equal. It means that you can't have a complex component. Otherwise, like this would be like a plus minus, like it's automatically just makes them different as long as that's non-zero. Yeah, so that's the idea behind this proof. Any questions about this proof at all? Yeah, this isn't something you have to memorize, but it's good to go through kind of seeing like how these how you can move things around, how they interact with one another. Right. So this is saying these like if S is a real symmetric n by n matrix, you can only have real eigenvalues, which is a really nice property. And then this eventually leads, so I'm not proving this theorem, and it's a really long theorem to prove, and it would be a lot more complicated than what we've done, and it would use theory that we haven't shown yet. But eventually this leads to kind of like one of the ultimate theorems in linear algebra, which is called the spectral theorem. And so the spectral theorem is telling you that symmetric matrices are pretty much as nice as possible, in the sense that it's saying that every symmetric matrix has the following factorization. So it's saying every symmetric matrix is diagonalizable with real eigenvalues that are going to make up your matrix lambda. And we also have that the matrix Q is going to consist of orthonormal eigenvectors. Right. So like orthonormal vectors, that was the whole point of Gram-Schmidt. Like those are particularly nice vectors. So it's saying like if you have a symmetric matrix, you have real eigenvalues, and the eigenvectors are give you an orthonormal basis. What's also nice is that if Q has columns given by orthonormal eigenvectors, that means the inverse of Q is just given by the transpose. So if you have orthonormal column vectors, it means that you have a symmetric matrix. We proved this, I think, in section 4.4 or something like that. So we proved this earlier. But yeah, so this is saying like we love working with symmetric matrices pretty much. And that's going to be the trend moving forward. Like the reason why I'm talking about this now is when you're doing singular value decomposition, you're only going to be looking at, like you're going to take a matrix and then you're going to construct a symmetric matrix that relates to it. And then you can apply the spectral theorem and it's going to make things good for you. Okay, so we've been really just thinking in terms of the case of distinct eigenvalues. The case of repeated eigenvalues is going to be postponed until we reach chapter 7. So we'll go through one application of, well, we're going to go through a lot of applications of the spectral theorem. But one of them is it introduces a notion of a square root of a matrix. It's kind of like an odd idea, I suppose. And so for this example, it's asking you to find the square root of the matrix S. So we're given some symmetric matrix. So we already know it's going to be diagonalizable with real eigenvalues, with orthogonal eigenvectors. So it wants you to find a matrix A, such as the square of A ends up being equal to S. And so it's maybe weird to have this idea of a square root of a matrix. Does anyone have an idea on how you would find the square root of a matrix? Kind of like, how are we going to solve this problem? It's not going to be taking the square root of each of the entries. Any ideas? Yeah, I mean, you want to do like the diagonalization, right? I mean, it's just this idea over again, where like if we know that S is diagonalizable, then we know that S. I'm going to use this notation. Like when I write Q instead of like I've been using X mostly for I can't remember. I think I did X and then lambda or something like that. When I write Q, I'm saying this is like a symmetric matrix. So because S is symmetric, well, I meant to say orthogonal. We know S is symmetric, therefore Q is an orthogonal matrix, and then you have the following, right? Just from the spectral theorem, we can say this. And this is really just equal to Q times lambda, and then you do like Q transpose, like the inverse and the transpose are equal because Q is orthogonal. And so the idea is still going to hold from what we were doing before, right? If I apply the 1/2 power here to S, which maybe seems a little bit odd, we can make it so this is going to be like the 1/2 power of lambda, and this is like the 1/2 power, well, the 1/2 power of lambda over again. And this is fine, right? Because if you have a diagonal matrix, say this is like 4, 0, 0, 9, and if I took the square root of this is just going to be applied to the diagonal. So this would be equal to like the square root of 4, 0, 0, and then the square root of 9, which would then be equal to 2, 0, 3. Because if I took this matrix and multiplied by itself, you'll just get 4, 0, 0, 9, right? So like when I do the square root of a diagonal matrix, it's really just doing the square root of the entries, and that's fine. Like there isn't an issue with that at all. So I don't know if this is like notation people actually use to denote like the square root of a matrix, but I'm just trying to draw a parallel to what we've seen before, where you can use diagonalization to understand the powers of your original matrix. Is what I'm getting at. Okay, and so this is the goal. I'm gonna just I kind of have it already written, but I'm gonna write it over again. So the goal is the following: we want to find Q and lambda such that we have the following. So such that we'll have like S is equal to Q lambda Q transposed, which would then imply that we have like S to the 1/2 power, which is equal to Q, and then lambda to the 1/2 power, and then you have Q inverse, or I'll write Q transpose over again. Right, so it's really just asking you to find the diagonalization. And then just kind of doing a problem that you've already done before, except now you have a 1/2 power instead of like a third power or something like that. So I'm going to kind of skip through the computation of the eigenvalues and the eigenvectors. There isn't anything particularly interesting that happens here. So you just subtract the diagonal by lambda and you take the determinant. And what you'll end up finding is that one eigenvalue is going to be equal to 3. And the other eigenvalue is going to be equal to 1. And then you'll look at the, so you'll plug in like lambda is equal to 3, lambda is equal to 1. You would find the null space of the respective matrices that you would get when doing that. And you would end up getting that one of the eigenvectors is going to be v1 is equal to 1, 1. So this is the eigenvector corresponding to 3. The other eigenvector is going to be v2, which is equal to -1, 1. And the solutions I go through more detail in case you don't know where these numbers are coming from, but we've done a number of examples like this before. So I'm just going to kind of get to the more interesting part, instead of doing the root computation. And so using these eigenvalues and eigenvectors, again, because this is symmetric, I'm saying this over and over again, but I'm trying to ingrain it in your head. Because this is symmetric and we have distinct eigenvalues, that guarantees these vectors are orthogonal to one another. And you can see if you did the dot product of v1 with v2, it would be -1 plus 1 times 1, which is equal to 0. So automatically they're going to be orthogonal, which makes things very nice. Because now we can say the following. So the diagonalization tells us that S is going to be equal to the matrix you get when you use the eigenvectors as your columns. So this is going to be 1, 1, and then minus 1, 1, times a diagonal matrix consisting of your eigenvalues, which is going to be 3, 0, 0, 1. And then this is going to be multiplied by the inverse. Oh, I do have to make a comment here. But it's going to be times the inverse. So it's going to be 1, minus 1, 1, 1. Inverse. And so I guess there is kind of a distinction that's going on here. So the inverse of this matrix, if you were to compute it, it is actually going to be different from the transpose. When they're writing out this Q here, they're assuming the column vectors are orthonormal, but these vectors aren't unit vectors. So like in order to make it so, like if you wanted to compute the inverse of this matrix as the transpose, you would have to take these vectors and make it so they're unit length, and then you'll take the transpose and that would be the inverse. But these aren't unit vectors. We just have an orthogonal vectors and not orthonormal vectors. So what ends up happening is when you eventually compute the inverse here, when you divide by the determinant, that introduces the effect of making things orthonormal. So like they end up coinciding with one another. But I'll just, so what ends up happening here is like it becomes 1, minus 1, 1, 1, 3, 0, 0, 1. And then this vector or this matrix here, if you want to find the inverse, the way we've been doing that is you divide by the determinant. So that's going to be 1 times 1 minus 1 times 1, which is going to introduce a 1/2. And then you flip the diagonal entries. It's the same in this at this point. Then you multiply the off diagonals by minus 1. So this is minus 1 and then 1. So it's kind of like you can see it's kind of like taking the transpose, but you have to incorporate this 1/2 due to the fact that these weren't orthonormal. So the two ways coincide. You can start by like finding the orthonormal basis and then using them for your column vectors or whatever. But you'd have to do it for both pairs. You have to do it for this one and this one. So I give like 1 over the square root of 2, 1 over the square root of 2. You multiply them, it gives you 1/2. I don't know. Maybe I shouldn't have said anything. Maybe it makes things more confusing. Anyway, so the main point though is this is what S ends up being equal to. And so if we take the square root of S, it's really just applying the square root to the diagonal. You ignore everything else. That's what we've proven before. So S to the 1/2 power. I'm going to bring the 1/2 out in front, I suppose. This is like 1/2, and then you have 1, minus 1, 1. This is going to be the square root of 3, 0, 0, and then the square root of 1, which I'm just going to write. I'm going to say it's the square root of 1, like this, just to illustrate that I applied the square root. And so that's all that's going on. It's pretty much the exact same problem we've already been doing. It makes things a little bit nicer, though, in the sense that we know these are going to be real values, so they're not taking like square roots of complex numbers. These could be negative, though, which would then mean you get complex numbers, but that's less of an issue. And so if you multiply all this out, you end up getting the following matrix. You end up getting the matrix, the square root of 3 plus 1, the square root of 3 minus 1, square root of 3 minus 1, and then the square root of 3 plus 1. So you still have a symmetric matrix, right? These two terms are equal to one another. And if you wanted to check that this is actually going to work out, this computation is a little bit ugly, but you could check and see that if you multiply this matrix by itself, it's going to end up being equal to the original matrix S that I ended up giving you. So if you multiply these two matrices, or like this matrix with itself, again, this is something you can check on your own, but it would look like this. So you would multiply the same matrix with itself over again. What ends up happening is this is going to be equal to 1 over 4. So you multiply the 1/2s with one another, and then you get 8, 4, 8, 4. Or I messed that up. 8, 4, 4, 8. Which is then equal to 2, 1, 1, 2. which was equal to S originally. So you can go through, it's kind of annoying to check because you can see there's going to be like some foiling that you need to do and things will cancel out. Eventually you end up getting like 8 times 1 over 4, which is equal to 2, so on and so forth. So it really isn't that different from other problems that we've done, even though it's like a fractional power, which makes it a little bit more odd. Any questions about this example at all? Yeah, I think the only thing that maybe it was like a little confusing was me going into like these are orthonormal when they're making these assumptions, whereas these ones, the eigenvectors, I haven't made them orthonormal, which made it so you have to compute the inverse in a more traditional. Okay, so that's it for section 6.4. This stuff is still going to be important though. Like we're still going to be working with these kinds of ideas in the upcoming sections as well. All right, so now we're going to be looking at positive definite matrices. We're still going to be talking about symmetric matrices. All right. Yeah, there's going to be extras probably in the second and last row, the second to last row and the last row. You can just throw them on the ground. Or you can I'll get them eventually. You can just throw them anywhere. Okay. Yeah, so kind of the idea behind these positive definite matrices is we looked at symmetric matrices and we saw that they had real eigenvalues. These positive definite matrices are going to ensure that your eigenvalues are going to be positive, which then means if you're taking a square root, you're not going to have complex numbers or anything like that. You're not going to have like the square root of -1 or anything like that. And so the big idea that's going to carry over into the future sections is this one right here. So I'm bringing attention to it. And I guess I'll bring attention to it in the future as well. But what's going to be really nice about these positive definite matrices is going to be the fact that if S is going to end up being equal to A transpose times A, this is something we're going to make use of when we're looking at this singular value decomposition later on. And really the main connection, this is like the general overview. I'm going to say this again, but the main connection between this singular value decomposition and diagonalization is that you're really just, to get the singular value decomposition, you're just applying diagonalization to matrices of the form of like A transpose times A, right? So in order to understand this singular value decomposition, you have to be able to understand the relation between A and then A transpose times A, and like how the theory of their like eigenvalues and eigenvectors relate to one another. And we've already proven one of the big results earlier in this class. Like we've shown before that the null space of A is equal to the null space of A transpose times A, which I'll review later on. That's kind of the larger overview of why this section is going to be important, as it's going to be essential for understanding singular value decomposition. Okay, yeah, so this section is going to concentrate on symmetric matrices that have positive eigenvalues. I like the way they said this in the book, I guess. So symmetric matrices, or symmetry, makes a matrix important. This extra property where all the eigenvalues are greater than 0 is going to make it truly special. So like when we say special, we don't mean, I'm just reading from the book at this point. So symmetric matrices with positive eigenvalues are at the center of all kinds of applications, as I've kind of been getting at. Such matrices are called positive definite. So there's kind of two definitions here. The only thing that changes from one definition to the other is they introduce the word or like the subword like semi. So the only difference is like an n by n matrix S is positive definite if S is symmetric and every eigenvalue of S is positive. So this is like strictly greater than 0. The next definition is pretty much the same, but with the addition of the word like semi-definite, it changes the word positive to non-negative. So it just means greater than or equal to 0. So that's the only difference between these two matrices, or like these two definitions. And again, this is something that you should remember. Whenever I'm defining something as being positive definite, it's baked in that S is going to be symmetric. So like it's a stronger type of matrix than being symmetric. It's going to be symmetric and it has additional properties. And so we're going to come up with a number of ways to classify or to determine whether or not our matrix is going to be positive definite or not. The most basic way is going to be showing that the eigenvalues are going to end up being positive. And so for this, this example is going to be like it wants you to show the following matrix is positive definite. So you just compute the eigenvalues and show they're greater than 0, which is something that should feel pretty comfortable doing. But we're going to have other ways of showing that a matrix is positive definite. That's going to be a little bit easier. So we just need to show the eigenvalues are greater than 0 here. So you need to show they're positive. And so, I usually skip the eigenvalue computation, but that's kind of all there is to this problem. So I'm going to go through it. So this is S, you do S minus lambda I, the determinant of that. So you do like the minus lambda on the diagonal, minus lambda along the diagonal. So this will give you 4 minus lambda times 4 minus lambda. And then you subtract by 3 times 3. So it's going to give you a minus 9. And so if you FOIL this out, and I like writing the lambda first. This is going to be lambda squared. Then you have minus 8 lambda. And then if you combine the constant terms together, this will be plus 7. So this ends up being equal to lambda minus 7 times lambda minus 1, which then implies that we have lambda is equal to 1 and lambda is equal to 7. You can see both of these are greater than 0, and so it checks out. So this is a positive definite matrix because both of the eigenvalues are greater than 0. Any questions about this example at all? Okay. Yeah, so that one's kind of like, you already know how to do that pretty much. There isn't really anything new. So we're going to find easier ways. You don't always want to compute eigenvalues for these things. Sometimes you want to just skip some corners. So we're going to come up with other ways to determine whether or not a matrix is positive definite. And this next page, I don't know. I didn't want to, it's pretty long. And this is just the idea of the proof. I already have it written out because I didn't want to spend 30 minutes writing it out in class. What I would say is you don't have to write any of this down, right? I printed off the packets before I wrote this down, and then I changed my mind and I didn't want to waste the paper. I would say you don't have to write any of this down. It's not really going to show up again. So I don't know. I'm just going to go through the idea, but you don't have to it's not going to show up on the exam or anything like that. It's more of just like the intuition behind the following. So this is going to give us an easier way to determine whether or not we have a positive definite matrix or not. So this proposition says that the signs of the eigenvalues of a symmetric matrix are going to be the same as the signs of the pivots. So this is saying that if you row reduce your matrix down to upper triangular form without multiplying anything by -1 or anything like that, then the signs of the pivots are going to tell you what the signs of the eigenvalues are going to end up being. So in other words, if you can show that all of the pivots are going to be positive, that implies that all the eigenvalues are going to be positive as well, which then cuts through, like you don't need to go through and calculate the eigenvalues, right? So if you have like a 100 by 100 matrix, finding the eigenvalues of that's a lot worse than reducing it to upper triangular form. Right, so this proposition proves this corollary, which is like the main takeaway. So the idea behind this proof, and again, I don't recommend you like copy this down or anything. I'm just going to say it out loud. So the idea is that if you have a symmetric matrix, using elimination matrices, it allows for simultaneous row/column operations during elimination. So if I had this matrix S, this is a symmetric matrix. We have 4, 3, 3, 4. I can multiply both sides by this elimination matrix. So this is an elimination matrix where you're applying like X and then you're really just multiplying this by x and kind of like adding it over here. And then I'm multiplying the other side by the transpose of this elimination matrix. And the main observation is that by doing this multiplication, I'm not changing the determinant at all, because this has determinant 1, this has determinant 1. And so we know that the determinant is like multiplicative, right? And so like this implies that the determinant of L times S times this like L transpose is equal to just the determinant of S. So by doing this multiplication by elimination matrices, it doesn't change what the determinant is going to be at all. But in multiplying these matrices together, you end up getting a matrix of the following form. So you see you get like some sort of quadratic form in the 2 entry, some linear functions. So it's still symmetric. On the off diagonal, you have linear functions and they have like a constant here. And we want to see what happens when we plug in various values for x. So for instance, if I plug in x is equal to 0, then there isn't going to be any effect that these elimination matrices have, because then you're just multiplying by the identity. So if you let x be equal to 0, this product is just going to be the original matrix that you have, which we know is going to be lambda is equal to 1 and 7. So you have those two eigenvalues. And then you can also think about what happens when I make the off-diagonal terms be equal to 0 as well. So if I plug in x is equal to 3 minus 4, or minus 3 over 4, the product would end up being the following diagonal matrix, where you have lambda is equal to 4 and 7 over 4. So these are the pivots, right? Like these are the two pivots. I always circle them in red, so I'm going to do it again here. All right, so these are the pivots of your matrix. You can see that they're both positive. And so we want to relate the positivity of these two pivots with the fact that these like eigenvalues are positive as well. And we're actually going to be using something called the intermediate value theorem from calculus, which is just saying, so like the idea here is that as x ranges from 0 to minus 3 over 4, you're going to be going through various eigenvalues. Like they're going to vary continuously from the fact that these are like continuous functions. And so the idea here is that in order for lambda to change signs, so in order to go from like positive to negative for one of these lambdas, it must equal 0 for one of the x values, because you can't just like skip past 0, right? If this is varying continuously, you have to hit 0 eventually. But this is going to be impossible, because when we're doing this multiplication, we're not changing the determinant. And if you get a 0 eigenvalue, it forces the determinant to be equal to 0. And so what we're saying is like the determinant can never be equal to 0, which means that the eigenvalues are never going to change sign. You can never go from positive to negative. And so what ends up happening is that the eigenvalues of S are always going to have the same signs as whatever the pivots of S are going to be as well. So that's the idea. In order to go through a general proof, it requires a lot more writing. I should have, in the print off, I should have had this like written down, because I don't like the idea of it just being blank. But this is the idea. You don't really, I'm not going to ask you about it again, but that's the gist of it. So the main takeaway is that if you have a symmetric matrix, it's positive definite if and only if its pivots are going to be positive. So at this point, there isn't really a point in actually computing the eigenvalues, because it's a lot easier to just determine like, oh yeah, the pivots are going to be positive here. It's easier to row reduce than it is to compute and solve like the polynomial that comes from setting the determinant equal to 0. Okay, so there's a couple of other checks. Oh yeah, are there questions about kind of like the idea that's going on here? Like why this is working out? Okay, so there's going to be other criteria in determining whether or not you have a positive definite matrix. I think pretty much all of them are going to be pretty important. I guess some of them are, I would say there's like 3 of them that are important, because like I think one of them kind of nullifies 2 others. And so the following statements are going to be equivalent to one another. If you took like principles of math, you should kind of understand what it means for one statement to be equivalent to another. But what this is saying is that if you have a symmetric matrix that has one of the following properties here, then it has to have all 5 of the properties at the same time. So it suffices to prove one of them to show that you have all 5 of them. And so when we have a symmetric matrix that has one of these 5 properties, it must mean it has all 5 of them. So these are like the various definitions that people use to say you have a positive definite matrix. So if you have all n pivots of S are positive, That's the same. I'm going to skip this one for now. This is the same as saying all n eigenvalues of S are positive, which is how we originally defined positive definite. It also means this matrix product is going to be positive, except that x is equal to 0. And then it also means that S can be expressed as A transpose times A for a matrix A with independent columns. So I'd say the three important ones are going to be 1, 4, and 5. This first one kind of makes the set like these two ones redundant, right? In the sense that it's much easier to do check this than it is to check these two. So I think the first one kind of makes 2 and 3 a little bit redundant, so you don't have to worry about them very much. When it's saying like the upper left determinants, I don't know if I want to say that much about it. If you have like a 3x3 matrix, I guess what it's saying by like this isn't like a definition that you have to really think about from the future onwards, but it was in the book, so I decided to include it. So it's talking about upper left determinants. It's saying like this determinant here, this is like a 1x1 determinant. This is going to be positive. And then you also have to have that this determinant is going to be positive. And then the 3x3 left determinant is the entire thing. So you have to choose, like you have to show all of those determinants are going to be positive. It just isn't really a practical way of doing things for the most part, especially if you have like a larger matrix, then you're doing like 5 determinants to prove one thing, and it's easier to just row reduce. So I'll say 1, 4, and 5 are the ones that you need to know. Let's see, how long does it take to finish this one? I want to see. I should probably stop here, to be honest. So in Wednesday's class, we'll prove 4 and 5, and then we should be able to go on to singular value decomposition. And there has been a new homework that's been posted. It should be shorter than the other ones. It's only like 7 problems. It should be a little bit.